You know, usually when we talk about the invention of the modern computer, there is a very specific, almost cinematic picture that comes to mind.
Oh, absolutely. Like this
Yeah.
highly dramatic, top-secret atmosphere.
Right, exactly. You are probably picturing these massive government laboratories, rooms just filled with towering walls of vacuum tubes glowing in the dark.
Yeah, and thousands of miles of tangled wiring everywhere.
Right, and a whole army of brilliant mathematicians in lab coats working around the clock. You think of Alan Turing at Bletchley Park or the ENXC project in the United States.
Huge coordinated efforts backed by basically unlimited wartime budgets.
Exactly. It's a story of colossal institutional effort.
Hmm.
But what if I told you that while all of that was happening, or actually even before some of that was happening, a guy who genuinely just hated doing his math homework was building the modern computer
In his living room.
in his parents' living room,
Echo.
entirely by himself? So today we are welcoming you to another deep dive. And our mission today is to uncover the story of Konrad Zuse.
And we're pulling this from a really comprehensive Wikipedia article detailing his life, which spanned from 1910 to 1995.
Yeah, Zuse was a German civil engineer, a pioneer, and honestly just an absolute maverick of computer science. So, okay, let's unpack this.
Let's do it.
Because I really need to know, how does someone completely cut off from the global scientific community, entirely unaware of what giants like Turing or von Neumann are doing, how does that guy end up building the world's first programmable computer?
It's a completely wild story, honestly. And what I really want you to take away from this deep dive isn't just, a dry timeline of how early computers were wired together.
Right.
I want us to look at the profound resilience of human innovation. We're going to explore how someone can push the absolute boundaries of technology under the most extreme, isolated, and frankly devastating circumstances imaginable.
So I feel like we have to start with his motivation, because usually we assume inventors are driven by this noble quest for human advancement or, I don't know, curing a disease, right?
Right, some grand vision.
Yeah. But for Zeus, it really seems like his driving force was just a severe allergy to boredom.
That is pretty much it, yeah.
So he studied engineering and architecture at the Technical University of Berlin, but he actually found those subjects incredibly tedious. He graduates as a civil engineer in 1935, and he gets this job as a design engineer at the Henschel aircraft factory. And this is where the frustration really sets in.
Because, if you think about it, aircraft design in the 1930s meant doing structural calculations. Yeah, hours and hours of routine, repetitive, manual mathematics by hand. And Zeus absolutely despised this.
I mean, who wouldn't?
Right. He basically realized that the human brain just isn't built to crunch numbers all day. It's a total waste of intellect. He recognized that calculation is fundamentally a mechanical process.
Right. It's just following a strict set of rules over and over.
Exactly. And therefore, a machine should be doing it. So he started theorizing a way to make a machine do the boring parts of his job.
Which means he decides to just build one himself. So, starting in 1936, he sets up a workspace in his parents' apartment in Berlin. They eventually move to a flat on Methwesselstrasse 10, and right there in the living room, he builds his first machine, the Z1.
In the living room.
Yeah, between like the sofa and the dining table. And the source notes it was a floating point binary mechanical calculator containing roughly 30,000 metal parts.
That is a lot of metal.
It is. But wait, let's pause here for a second because I really need to understand what that actually means. Like, how do you do math with metal? We think of computers as electrical, right?
Yeah.
So how does a purely physical mechanical machine process binary code?
It is a great question because it really forces us to rethink what a computer actually is at its core. Binary just means a system of ones and zeros.
True or false? Open or closed?
Exactly. In a modern computer, that is done with invisible electrical switches. But Zeus didn't use electricity for the logic. He used thin metal plates stacked on top of each other.
Okay, I'm picturing that.
So imagine two metal plates with a tiny slot cut into them. If the slots line up perfectly, a little metal pin can drop through.
Oh, wow. Okay.
And that pin dropping through, that's a 1, a closed circuit. But if a plate slides slightly to the side, the slot is blocked.
The pin can't drop.
Right, the pin can't drop, and that is a 0. By arranging 30,000 of these sliding plates and pins, he created physical logic gates. The machine could literally shift metal around to add and subtract numbers.
Okay, so it's almost like setting up a giant, incredibly complex maze of train tracks. If a piece of metal slides to the left, the track is open, which is a 1. If it slides right, it blocks the path, which is a 0.
That is a perfect way to visualize it.
He was physically building the logic of a Microsoft Excel spreadsheet out of basically interlocking metal erector set pieces.
Exactly. But to control those train tracks, he needed a way to feed instructions into the machine.
Right, you have to tell it what math to do.
Right. Modern computers use code. Early computers used paper punch cards. But Zuse couldn't afford custom punch cards.
Because he's just a guy in his living room.
Right. So he used discarded 35mm camera film.
No way, camera film.
Yeah. He would physically punch holes into the film. A gear would pull the film through the machine. And wherever there was a hole, a tiny metal pin would drop through it.
Oh, and that triggers the whole sequence of sliding plates.
Exactly.
That is just brilliant problem solving. But what really stands out to me is that he's doing this entirely in a vacuum. I mean, he's figuring out how to build physical logic gates with 0 outside help.
What's really fascinating here is the sheer intellectual isolation of what he was doing. In 1937, Zuse actually submitted patents that anticipated the famous von Neumann architecture.
Remind us what that is again?
It's the basic design concept behind almost every computer today, where programs and data are stored in the same memory.
Oh, wow.
Yeah, and he was doing this completely independently of the leading academic circles of his day. He had no idea what anyone else was working on.
It really proves that major paradigm shifts don't always come from these well-funded collaborative universities.
No, sometimes they come from a single person who just really wants to automate their own tedious workload.
True. But as clever as that living room setup was, 30,000 janky hand-cut metal parts jamming up constantly isn't exactly sustainable.
Not at all.
You can't really build the next generation of computing in your mom's living room, especially when the world is suddenly on the brink of a massive global conflict.
Right.
He hit a wall, he needed space, and honestly, more importantly, he needed money, which forces him into a very different and much darker environment.
Yes, the onset of World War II shifts his focus drastically. Zuse gets called to military service, but he actually manages to get government funding through the Aerodynamic Research Institute.
Okay.
So he begins building machines for the military, specifically the S1 and S2 computing machines. These were used to compute aerodynamic corrections for the wings of radio-controlled flying bombs.
And strictly from an engineering standpoint, the sources say the S2 was a massive leap because it featured an integrated analog-to-digital converter.
Yes, that was a huge deal.
But let's clarify that for the listener, because analog to digital gets thrown around a lot in tech today. What did that actually mean for a physical machine in the early 1940s?
Well, think about the real world. Wind resistance pushing against an aircraft wing is an analog measurement. It's continuous physical data. It constantly fluctuates.
Right.
A computer, however, only understands digital data. Discrete, absolute ones and zeros.
It needs hard numbers.
Exactly. So the S2 was the first process-controlled computer because it could physically measure those continuous analog dimensions from the aircraft wings and automatically convert them into digital binary code.
Oh, so the program could actually process it.
Right. It bridged the messy physical world and the precise digital world.
Which paves the way for what becomes his masterpiece at the time. By May 1941, he presents the Z3. And this was the world's first programmable, fully operational computer.
The first in the world.
But he didn't use pristine, custom-made parts. He built the calculation unit and the memory using discarded telephone relays.
Literal garbage he collected.
Yeah. Old phone parts. But this takes us to a really complicated part of the story. Because it is the early 1940s in Germany, and his work is objectively fueling the Nazi war machine.
Yes, it is.
Now, we want to be very careful to just report the facts here without endorsing the context. The source material notes that Zuse was never a member of the Nazi Party, but he also showed no qualms about his work at the time.
That is correct. We are strictly relaying his historical reality and his own later words here. Much later in his life, Zuse reflected on this dynamic, describing it as the Faustian bargain that scientists and engineers inevitably face.
No deal with the devil.
Essentially, yeah. He argued that in modern times, the best minds usually have to choose between doing their work for questionable military or business interests or simply not pursuing their life's work at all.
And he made the choice to take the funding and keep building his machines.
He did.
And regarding the technology itself, this is where the story takes a really interesting turn. The Z3 is universally recognized today as the first Turing-complete computer, meaning Theoretically, it could compute anything that can be computed, given enough time and memory. But wait, here's where I push back. Did Zuse even know what Turing completeness was?
Nope.
Like, was he reading Alan Turing's theoretical papers while he was wiring up old phone relays?
Not at all. He had no idea what Turing completeness was.
That is wild.
He only cared about practical results. He wasn't trying to solve some grand philosophical puzzle of mathematics like Alan Turing was. Zuse was a practical engineer dealing with the brutal realities of wartime shortages.
Which perfectly explains the Schnapside incident.
Oh, yes.
The source mentions a coworker of his, Helmut Schreier, who suggested they use electronic vacuum tubes instead of physical telephone relays to make the Z3 faster.
A very smart suggestion, theoretically.
Right, but Zuse rejected it.
Yeah.
He called using vacuum tubes a Schnapside, which basically translates to a crazy, drunken idea.
Oh.
Why would he reject the exact technology that eventually made computers lightning fast?
Because theoretical perfection doesn't win out when you are building something in a resource-starved war zone.
Fair point.
Vacuum tubes were fragile, they burned out constantly, and they were nearly impossible to get in wartime Germany. Discarded telephone relays, on the other hand, while they were slower and physically noisy.
I read they clacked super loudly when they switched.
Oh, they were incredibly loud. But they were robust and readily available. He wasn't trying to build a platonic ideal of a computer. He was trying to solve immediate aerodynamic problems using the literal scraps available to him.
Practical engineering over theory.
Exactly. Sometimes engineering has to outpace theoretical perfection just to get the job done.
But relying on physical, clacking hardware in a war zone comes with an incredibly high risk. Because hardware is fragile, it can be shattered.
Yeah, it can.
By late 1943 and early 1944, Allied air raids start heavily devastating Berlin. And the reality of the war finally catches up to him. Zuse's workshop is destroyed. His parents' flat is destroyed.
Everything you'd worked on.
The Z1, the Z2, and the Z3, all of them completely obliterated in the bombings.
It is a devastating loss. I mean, the physical culmination of years of labor is just gone in an instant.
It's just a rubble.
Yeah. The only machine that survives is the partially finished Z4, which he had luckily begun in a different location. In February 1945, just days before massive bombings completely leveled that specific area of Berlin, the Z4 is packed up and moved out of the city.
Wow, just in time.
Just in time.
Mm-hmm.
And Zuse eventually flees to the rural Allgäu region in southern Germany.
So picture his situation now. He's hiding in a rural village during the extreme deprivation of post-war Germany. There are no spare parts, there is barely any food, and there certainly is no electricity to run massive experimental computing machines.
Right. Physical invention is basically impossible at this point.
Exactly. He can't physically build computers anymore, so what does he do? He turns to pure theory.
Yep.
Between 1943 and 1945, out of pure necessity, he develops Planckkuchel, or plan calculus, and the source explicitly calls this the world's first high-level programming language.
It was.
But hold on, let's back up for a second. How do you invent software when you don't even have a computer to run it on? What does inventing software on paper even look like?
That is the absolute genius of it. Up until this point, programming a computer meant writing in machine code.
Which means what, exactly?
You had to physically understand the hardware. You were writing literal strings of ones and zeros, or in many cases, physically rewiring cables on a plug board to change the machine's function.
Oh, wow. So you were practically rebuilding the machine for every new task.
Exactly. It was incredibly complex, error-prone, and tied specifically to the physical machine you were using at that moment. Zuse realized that for computers to ever be truly useful on a wide scale, humans needed a higher-level language.
Okay, so it's the difference between having to know how to physically build and tune a car engine from scratch every single time you want to go to the grocery store,
Right.
versus just sitting in the driver's seat, pressing a pedal, and letting the mechanics handle themselves behind the scenes.
Precisely. Planckkuchel was about writing logical statements in a way that made sense to human mathematics. Things like, if this condition is true, then execute this operation.
Like modern coding.
Exactly like modern coding. Zuse envisioned a system where a human could write this high-level logic, and a separate program, what we now call a compiler, would translate that human logic down into the ones and zeros the machine needed.
He was entirely separating the discipline of software from the discipline of hardware.
Yes. And to prove it worked, he didn't just write simple math equations.
Oh, I love this part.
He used Planckkuchel to write the first real computer chess engine.
On paper.
On paper. He was writing conditional logic for knight moves and pawn captures years before a machine even existed that was capable of running it.
Which just demonstrates his absolute conviction that computation wasn't just about crunching aerodynamics for wings anymore.
No, it was about processing general logic and rules.
Yeah.
And he maintained this incredible focus amidst total societal collapse.
Yeah, speaking of that collapse, I have to mention this detail because it is so incredibly human. In January 1945, while the country is literally falling apart, he marries Gisela Brandes.
And he insists on a noble ceremony.
Yes. He somehow procures a horse carriage, shows up wearing a top hat and a tailcoat, right in the middle of a collapsing war zone.
It's amazing.
It really speaks to this unyielding insistence on maintaining order and structure, right?
Right.
Whether that is in his personal life or in his code.
It really does. But, after the war, that strict adherence to his own structure hit a wall with academic bureaucracy.
Oh, yeah, it's classic.
He tried to submit his work on Plankalkül as a PhD thesis to the University of Augsburg. And keep in mind, this is a document that essentially invents the concept of high-level programming languages.
It is a historically priceless document, and the university rejects it.
Yes, they do.
Why? Because Zuse simply forgot to pay the 400 Deutschmark enrollment fee.
Such a trivial detail.
And the best part is, he didn't even fight it. He just moved on. For him, the validation of the academic establishment wasn't the goal. The goal was the work itself.
And as Europe began to rebuild, Zuse finally got the chance to turn his work into a viable business. He founded one of the earliest computer companies, Zuse KG.
Okay, so he finally goes commercial.
He does. And in 1947, a fascinating historical crossover happens. Zuse finally meets Alan Turing at a colloquium in Göttingen.
That is like a comic book crossover event for computer scientists.
Truly, you had these two independent titans of computing who arrived at the exact same destination from completely different paths, finally in the same room.
Did they talk about Turing completeness?
Probably. And Zuse's practical engineering-first approach really pays off in the post-war era. By 1950, he finishes the surviving Z4 and delivers it to the ETH Zurich.
The Federal Institute of Technology in Switzerland.
Right. And it works perfectly. It becomes the only working digital computer in Central Europe at the time, and essentially the first commercial computer in the world.
He goes on to invent other machines, too, like the graphomat plotter in the 50s and 60s, which actually becomes famous in the early computer art world.
Yeah, he never really stopped inventing.
But as he gets older, his mind seems to transcend physical hardware entirely.
Yes, his trajectory shifts heavily. He goes from the deeply practical constraints of discarded telephone relays to the incredibly abstract and philosophical.
Which leads us to 1967.
Right, in 1967, and later expanded in his 1969 book, Rechnender Raum, which translates to calculating space.
Great title, by the way.
It is. He proposes the concept of digital physics.
Okay, if you're listening to this and wondering how we jump from a mechanical 1940s calculator to digital physics, just stick with us, because the logic actually makes a strange kind of sense. But you have to unpack this for us.
I will do my best.
The source says he theorized that space is essentially a cellular automaton. What does that even mean?
Okay, think of a digital screen, or even a video game like Minecraft.
Okay, I'm with you. Blocks and pixels.
Exactly. The world is made up of discrete pixels or blocks. A cellular automaton is basically a grid where each cell has a specific state, like on or off, black or white, 1 or 0.
Right.
And the state of every single cell updates step by step based on a set of strict mathematical rules regarding its neighboring cells.
Like a cascade of updates.
Exactly. Zuse suggested that the universe itself is not a continuous flowing physical reality, but rather a colossal computational structure.
Wait, really?
Yes. He was arguing that the universe is quite literally computing its next state, particle by particle, frame by frame, based on fundamental binary rules.
So he's saying the universe is effectively a giant computer program updating itself.
That was his theory.
That is such a massive intellectual leap. How does a guy go from building literal calculators out of old telephone parts in his living room, just so he doesn't have to do math homework, to theorizing that the entire cosmos is a giant cellular autopon?
Well, this raises an important question about the nature of the computational mindset.
How so?
Think about what he spent his life doing. Once Zuse learned to break down complex, real-world phenomena, like the aerodynamics of an aircraft wing, into discrete binary values of 1s and 0s, it fundamentally changed how he perceived reality.
Oh, I see. When all you have is a binary hammer, everything looks like a digital nail.
Exactly. When you spend your entire life building machines that successfully simulate reality through computation, It is perhaps inevitable that you start to wonder if reality itself is just a simulation running on a grander machine.
He literally couldn't stop seeing binary code in the very fabric of existence.
Exactly.
It is an incredible evolution of a single human mind. Later in life, he builds a mechanical helix tower to demonstrate more physical computing concepts. He actually rebuilds the Z1 from memory because the original was bombed.
Which is an insane feat of memory.
Totally. And he eventually retires as a painter who signs his works under the pseudonym Kuno C.
The man lived a dozen lifetimes.
He really did. So to summarize this journey for you listening, Konrad Zuse proves that the digital age wasn't just born in massive, well-funded Allied laboratories with unlimited budgets.
No, it wasn't.
It was also born in a Berlin living room out of a visceral hatred for repetitive math. It was built from camera film and discarded garbage. And it was forged through near-total intellectual isolation and the absolute devastation of war.
And looking back at that isolation leaves us with a really fascinating what-if scenario.
Oh, I love a good what-if.
The computer scientist Donald Knuth once proposed a thought experiment based on Zuse's life. He asked, what would the timeline of modern computing look like if the bombings hadn't destroyed Zuse's workshop?
Right, if the Z3 had survived.
Exactly. Or what if his Planck-Halkuhl thesis had been formally published, that silly enrollment fee was paid, and his ideas for software were adopted by the global scientific community in the 1940s?
That changes everything.
We might have had high-level software decades earlier. Yeah. The entire trajectory of the information age could have been fundamentally altered.
That is wild to think about. We could be living in a completely different technological timeline right now. And it leads me to one final thought for you to mull over after this deep dive.
Let's hear it.
Zuse's concept of calculating space suggests that the entire universe is just a computational structure, right? A massive grid of data updating frame by frame based on strict mathematical rules. If the universe is really a massive computer running a continuous algorithm, as the man who built the first programmable computer came to believe, then what does that make us? In the grand architecture of the cosmos, are we the hardware, are we the software, or are we just a bug in the code?